And now in this lecture we'll answer on two questions. In the first question we will find out the area of this semicircle that is inside quarter circle A or B. In the second question we will find out the area of this green shape that is inside rectangle ABCD. So we start with the first question. In the drawing we have quarter circle A or B. We know that AO equals to 5 units in Islam. That is to say the radius of this quarter circle equals to 5. And inside this quarter circle A or B we have this semicircle, and our mission is to find out the area of this semicircle. So first of all we will define the center of this semicircle. This point is point C. Likewise, we will define the touching point between the quarter circle and the quarter circle, and the semicircle. This point is point F. We will define the touching point of the quarter circle with the semicircle. This point is point G. We will define the point of tendency of tangent AO with this semicircle. This point is point H. And finally, we will define the point of tendency of tangent BO with this semicircle. This point is point L. In addition, we will define the radius of this semicircle as x. Therefore, CF equals to CG, they are both the area of this semicircle, that is equals to x according to our definition. So CF equals to x, and CG also equals to x. In the next step, we will join point C and L together by a straight line. CL is the radius of this quarter circle, that is equal to x. We will join point C and H together by a straight line. CH is also the radius of this quarter circle, is equal to x. So here we have the radius CL. The radius CL is drawn from point L, that is the point of tendency of tangent BO with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CH that equals to x. The radius CH is drawn to point H, that is the point of tendency of tangent AO with this semicircle. Whenever your radius is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we can either quadrangle CH or L. Inside this quadrangle CH or L, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule. that states that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth incident angle must be equal to 90 degrees in its sides. So inside quadrilateral CHOL, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral CHOL as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CHOL, side CH must be equal to the opposite side OL. But CH is x, therefore OL must be also equal to x. Likewise, according to the same rule, the same rectangle CHOL, side CN must be equal to the opposite side OH. But CN is x, therefore OH is also equals to x. So if we found out that quadrilateral CHOL is not a rectangle but a square, well, because of the fact that all of its sides are equal to each other, each side of this square equals to x. In the next step, we will join points O and C together by a straight line. By joining points O and C, we can do the right and associated triangle, triangle CLO. So we copy this right and associated triangle CLO in a new page, and we will implement the Pythagoras theorem with this right triangle CLO. Here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right and associated triangle, triangle CLO. According to the Pythagoras theorem, in this right triangle CLO, CO square equals to CL square plus LO square. So I'll write it down. CO square, that is the square of the hypotenuse, equals to CL square plus LO square. CO is the missing side, so we leave it as it is. So CO square equals to CL square. CL is x, therefore CL square is x square plus LO square. LO is also x, therefore LO square is x square. So in total, CO square equals to x square plus x square plus x square, that is 2x square. So if we found out that CO square equals to 2x square. Here we take a root out of this equation and finally get that CO, the length of the hypotenuse CO, is equals to the square root of 2 times x. So here CO equals to the square root of 2 times x units in its length. Point O is the center of the quarter circle. So from this point O, that is the center of the quarter circle, we have line segment OC that bisects chord FG. Why line segment OC bisects chord FG? Because of the fact that CF equals to CG equals to x. Each half equals to x. So line segment CO bisects chord GF into 2 halves. Each half equals to x. and therefore we can implement the rule 7. Okay, quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment will be also perpendicular to that chord. So in the drawing we have a circle. This is point O, that is the center of the circle. From this point O, that is the center of the circle, we have line segment OM that bisects chord AB. That is to say, MA equals to MB. So whenever you have a line segment that bisects the chord in any question, you can implement rule 7. And according to this rule 7, line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 7. So I can actually implement rule 7 in our drawing. Why? Because in our drawing, from the center of the quarter circle, that is to say from point O, we have line segment OC that bisects chord FG. Therefore, all the requirements of rule 7 are satisfied. Therefore, we can implement the rule 7. According to rule 7, line segment OC will be also perpendicular to chord FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. We know that the radius of this quarter circle equals to 5 because AO is the radius of the quarter circle that equals to 5. We join points O and F together by a straight line. What is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and ends at point F, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle is equals to 5 units in its length. In the next step, we'll copy the right and green triangle CFO in a new page, and we'll implement rule 7 on this right triangle CFO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the version from Pythagoras theorem. So actually, this is the right angle triangle CFO that I covered from the original drawing. The hypotenuse FO equals to 5 units in its length, CF equals to x, and CO equals to the square of 2 times x units in its length. According to the Pythagoras theorem, in this right triangle CFO, FO squared, that is the square of the hypotenuse, must be equal to CF squared plus CO squared. So I'll write it down. FO squared equals to CF squared plus CO square. FO is 5, therefore FO square is 5 squared, that is 25, and it is equals to CF squared. CF is x, therefore CF squared is x squared plus CO squared. CO is square root of 2 times x, therefore CO squared is square root of 2 times x squared, that is 2x squared. So in total we found out that 25 equals to x squared plus 2x squared, x squared plus 2x squared is 3x squared. So if we found out that 25 equals to 3x squared, here we divide this equation by 3, and finally we get that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. We know that the radius of this semicircle is x, therefore the area of this semicircle must be equal to pi x squared over 2. So write it down, the area that we are looking for is the area of the semicircle. That is actually equals to pi x squared over 2. So it is pi over 2 times x squared, and x squared is 25 over 3, therefore we substitute x squared in this equation by 25 over 3, and finally we get that the area of the green shape in total equals to, in the numerator we have 25 pi, in the denominator we have 2 times 3, that is 6. So actually found out that the area of the semicircle equals to either 25 pi over 6 square units, or in terms of numbers, this equals to 13.09 square units. Okay, again, we found out that the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, it is equals to 13.09 square units. So we finished with the first question. In the next step, I present to you the second question and we answer on it. Our mission in the second question is to find out the area of this grand shape. So, in the drawing, we have rectangle ABCD. Side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD, we have this semicircle and this quarter circle. Again, our mission is to find out the area of this grand shape. So, first of all, we will define the radius of this quarter circle BC as x. So the radius of this quarter circle equals to x according to our definition. BC is the radius of the quarter circle. We know that all the angles in a rectangle, inside the rectangle, are right angles. And therefore this angle that inside rectangle ABCD equals to 90 degrees in its size. In addition, we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 5, therefore DC must be also equal to 5 units in its length. According to the sum rule that says that the opposite sides of a rectangle are equal to each other, so in rectangle ABCD, side BC must be equal to the opposite side AD, but BC is x, therefore AD must be also equal to x. AD is one side of rectangle ABCD, but AD is also the diameter of this semicircle. So we know that the diameter of this semicircle equals to x. If the diameter equals to x, it means that the radius of this semicircle must be equal to half of it. That is to say, it must be equal to x over 2. So the radius of this semicircle equals to x over 2 units in its length. We will define the radius, we define the center of this semicircle, this point is point O. So the radius OY of this semicircle equals to x over 2 units in its length. And the radius OD also equals to x over 2 units in its length. So in the drawing, we have an external arch between this semicircle and this quarter circle. That is to say, they touch each other externally at this point. We define their touching point, this point, as point S. Whenever you have an external arch between two circles, or semicircles, or quarter circles, we can implement rule 10. So I will click quickly on rule 10, and we'll implement rule 10 in our drawing. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching point. So in the drawing we have two circles, and they touch each other at this point externally at point P. So they have an external arch between them at point P. The center of this circle is at point O. The center of this circle is at point M, and the straight line that connects their centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, according to this rule 10, OPM is one straight line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, we have an external arch between the semicircle and the quarter circle at point S. The center of this semicircle is here at point O. The center of this quarter circle is here at point C. And the straight line that connects the centers together is of course the straight line OC. And this straight line OC must pass for point S, that is their touching point. Again, the straight line OC must pass for their touching point, that is point S. Or OSC is one straight line. Again, OSC is one straight line. So we join points O and C together by straight line, and according to rule 10, the straight line OC must pass through point S, that is their touching point. So you can see from the drawing that the straight line OC definitely passes for point S, that is their touching point. The touching point of the semicircle with the quarter circle. Okay, so if OSC is one straight line, it means that OC must be equal to OS plus SC. So I write it down. OC equals to OS plus SC. So OC equals to OS. What is the definition of line segment OS? Line segment OS starts from point O, that is the center of the semicircle, and then at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OS is the radius of this semicircle, that is equal to x over 2 units in its length. So you can write here that OS equals to x over 2 plus SC. SC is the radius of this quarter circle, that is equal to x according to our definition. Why? Because it starts from point C, that is the center of the quarter circle, and then at point S, that is the point of the quarter circle itself. Therefore, SC is the radius of the quarter circle, that is equal to x. So here, SC is x. So in total, we should find out that OC equals to x over 2 plus x, that is 1.5x, or 3 over 2 times x units in its length. So OC equals to 3 over 2 times x units in its length. This is line segment OC, and the length of the line segment OC is 3 over 2 times x units. So in the next step, I'll copy the right triangle ODC in a new page, and we'll implement the Pythagoras theorem on this right triangle, triangle ODC. Here by PT is a version for Pythagoras theorem. Side OD equals to x over 2 units in its length. Side DC of triangle ODC equals to 5 units in its length. And we just find out that the length of the hypotenuse OC is 3 over 2 times x units. So actually, this is the right triangle ODC that they call it from the original drawing according to the Pythagoras theorem. And this right triangle ODC, OC squared, that is the square of the hypotenuse, equals to OD squared plus DC squared. So I write it down. OC squared equals to OD squared plus DC squared. OC equals to 3 over 2 times x units in its length. Therefore, OC squared is 9 quarters times x squared. And it is equals to OD squared. OD is x over 2, therefore OD squared is x squared over 4 plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total we found out that 9 quarters x squared equals to 1 quarter x squared plus 25. Here we subtract x squared over 4 from this equation, and we get that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared. Here we have x squared over 4 minus x squared over 4 is 0, so we're left only with 25. It is equals to 25. 8 over 4 is 2, so this expression equals to 2x squared equals to 25. Here we divide this equation by 2 and finally get that x squared equals to 25 over 2. X squared equals to 25 over 2. We take a root out of this equation and finally get that x equals to the square root of 25, that is 5 over square root of 2. Okay, again, I actually found out that x equals to 25 over 2 and x equals to 5 over square root of 2 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Again, the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. So I write it down. The area of the green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Because again, I should found out that the area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. What is the area of rectangle ABCD? the area of rectangle ABCD equals to the length of the rectangle times the width. The length AB is 5, the width BC is x, therefore the length times the width is 5x. So the area of rectangle ABCD equals to 5x minus the area of this semicircle. What is the area of this semicircle? The radius of this semicircle is x over 2, and therefore the area must be equal to pi x over 2 squared divided by 2. So the area of the semicircle equals to pi times x over 2 squared divided by 2 minus the area of this quarter circle. What is the area of this quarter circle? The radius of this quarter circle equals to x, and therefore the area must be equal to pi x squared over 4. So I can know the area of the quarter circle equals to pi x squared over 4. So actually the value of this expression is equals to the area of the green shape. What is the value of this expression? This expression equals to 5x. Here we have x over 2 squared is x squared over 4. So in total this expression equals to minus pi x squared over 4 times 2 minus pi x squared over 4. So the area of the green shape equals to 5x. Here we have minus pi x squared over 4 times 2. 4 times 2 is 8, so in total this expression equals to minus pi x squared over 8. Here we have minus pi x squared over 2. Here we multiply this expression, both the numerator and the denominator of this expression, by 2. And finally we get that this expression will be equal to minus 2 pi x squared over 8. So the area of the green shape in total equals to 5x minus pi x squared over 8 minus 2 pi x squared over 8. Minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So if we found out that the area of the green shape in total equals to 5x minus 3 pi x squared over 8. But we have already found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2 units in its length. Therefore, we can substitute x in this expression by 5 over square root of 2, and we can substitute x squared in this expression by 25 over 2. We'll do it now, and we get that the area of the green shape in total equals to 5x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total we found out that the area of the green shape equals to, here we have 5 times 5 is 25, so in total this expression will be equal to 25 over square root of 2 minus 3 pi over 8 times 25 over 2. Here we have in the numerator minus 3 pi times 25 is minus 75 pi. In the denominator we have 8 times 2, that is 16. So in total this expression equals to 75 pi over 16. So in total we found out that the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units in its length. The value of this expression is actually equals to 2.95 square units. So if we found out that the area of this green shape equals to 2.95 square units. So we finished the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our mission was to find out the area of this semicircle that is inside quarter circle A or B. So in the drawing we have quarter circle A or B. We know that the radius of this quarter circle AO equals to 5. Inside this quarter circle A or B, we have this semicircle, and our mission is to find out the area of this semicircle. So first of all, we define the center of this semicircle. This point is point C. We define the touching point between the quarter circle and the semicircle. This point is point F. We define the second touching point between the semicircle and the quarter circle. This point is point G. Likewise, we define the point of tendency of tangent BO with this semicircle. This point is point L. And finally, we define the point of tendency of tangent AO with this semicircle. This point is point H. In addition, we define the radius of this semicircle as x. Therefore, CF equals to CG, both the radii of this semicircle, is equals to x according to our definition. So CG equals to x and CF also equals to x. In the next step, we join point C and L together by a straight line. CL is of course the radius of this quarter circle, that is equals to x according to our definition. Likewise, we join point C and H together by C and H together by a straight line. CH is also the radius of this semicircle, that is equals to x. So here we have the radius CH that is on to the radius CL of this semicircle that is on to point L, that is the point of tendency of tangent BO in this semicircle. And whenever you have a radius that is on to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CH that is drawn to point H, that is the point of tendency of tangent AO with this semicircle. And whenever you have radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we get the quadrilateral CHOL. Inside quadrilateral CHOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral CHOL, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral CHOL as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CHOL, side CH must be equal to the opposite side OL. But CH is x, therefore OL must be also equal to x. Likewise, according to the sum rule, in the sum rectangle CHOL, side CL must be equal to the opposite side OH. But CL is x, therefore OH must be also equal to x. So actually found out that quadrilateral CHOL is not a rectangle but a square because of the fact that all 3 sides are equal to each other. Each side of this square is equal to x. In the next step, we join points O and C together by a straight line. By joining points O and C, we get the right and associated triangle CLO. In the next step, I copy this right and associated triangle CLO in a new page, and we implemented the pedagogical theorem on this right and associated triangle CLO. So actually, this is the right and associated triangle CLO that I copied from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle is CO, therefore the square of the hypotenuse is CO square, and CO square must be equal to CL square plus LO square. CO is the missing side, so we leave it as it is, so CO square equals to CL square. CL is x, therefore CL square is x square plus LO square. LO is also x, therefore LO square is x square. So in total, CO square equals to x square plus x square, that is 2x square. So CO square equals to 2x square. Here we took out of this equation and found out that the missing hypotenuse, the length of the hypotenuse CO is square root of 2 times x units in its length. So actually this is CO, that is equals to the length of CO is square root of 2 times x units. So here we know that point O is the center of the quarter circle. So from this point O that is the center of the quarter circle, we have line segment OC that bisect chord FG. Why line segment OC bisect chord FG? Because of the fact that line segment OC divides chord FG into two halves. Each half equals to x. CF equals to x and CG equals to x. So line segment OC, that is one from point O, that is the center of the quadrilateral. That is the center of the quadrilateral. Line segment OC bisects chord FG. And therefore, you can implement here rule 7. Whenever you have a line segment that is drawn from the center of the circle and bisect the chord, you can implement rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment is perpendicular to that chord. So in the drawing, we have a circle. This is point O, that is the center of this circle. From this point O, that is the center of the circle, we have line segment OM that bisects chord AB. That is to say, line segment OM divides chord AB into two halves. Each half here, AMA equals to MB. Okay? So we have we know that line segment OM bisects chord AB. So whenever you have a question, if a line segment that is on from the center of the circle and it bisects the chord, you can implement rule 7. And according to this rule 7, line segment OM will be also perpendicular to chord AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, from the center of this quarter circle, that is to say from point O, we have line segment OC that bisects chord FG. That is to say, line segment OC divides chord FG into two halves. Each half equals to x. CF equals to x and CG also equals to x. So all the requirements of rule 7 are satisfied, and therefore we can implement rule 7. According to rule 7, line segment OC will be also perpendicular to chord FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. In the next step, we join points O and F together by side line. We know that the radius of this quarter circle is 5 because AO equals to 5. What is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and ends at point F, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle that is equals to 5 units in its length. In the next step, I copied this right green triangle FCO in a new page, and we implemented the Pythagoras theorem of this right green triangle FCO. This is the right green triangle FCO that I copied from the original drawing. Side FC equals to x units in its length, side CO equals to square root of 2 times x units in its length, and finally the hypotenuse FO equals to 5. According to the Pythagoras theorem, in this right triangle CFO, FO squared, that is the square of the hypotenuse, must be equal to FC squared plus CO squared. Again, FO squared equals to CF squared plus CO squared. FO is 5, therefore FO squared is 5 squared, that is 25, and it is equals to CF squared. CF is x, therefore CF squared is x squared, plus CO squared. CO is square root of 2 times x, therefore CO squared is square root of 2 times x squared, that is 2x squared. So in total, we found out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So 25 equals to 3x squared. Here we divided this equation by 3, and we found out that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. What is the area of this semicircle? We know that the radius of this semicircle is x. Therefore, the area of this semicircle must be equal to pi x squared over 2. Again, the area of the semicircle equals to pi x squared over 2. So the area of the semicircle equals to pi over 2 times x squared. And x squared is 25 over 3. Therefore, we substitute the x squared in this equation by 25 over 3. And we found out actually that the area of the semicircle equals to pi over 2 times 25 over 3. So this expression equals to 25 pi over 2 times 3, that is 6. So in total, this expression equals to 25 pi over 6. So actually found out that the area of the semicircle equals to either 25 pi over 6 square units. Again, it is equals to either 25 pi over 6 square units, or in terms of numbers, it is equals to 13.09 square units. So And again, the area of this semicircle equals to either 25 pi over 6 square units, so in terms of numbers, the area of this semicircle equals to 13.09 square units. So we finished with the first question. In the next step, I actually presented to you the second question, and we solved the second question. Our mission in the second question is to find out the area of this green shape. So in the drawing, we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD, we have this semicircle and this quarter circle. And they touch each other externally at point S. Again, our mission is to find out the area of this green shape. So first of all, we define the radius of this quarter circle as x. Therefore, that is to say, BC, that is the radius of this quarter circle, equals to x units in its length. We know that all the angles inside any rectangle are right angles. Therefore, this angle equals to 90 degrees in its size. We also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5. Likewise, according to the same rule, in the same rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. AD is not only one side of rectangle ABCD, but AD is also the diameter of this semicircle. So, note that the diameter of this semicircle AD equals to x units in its length. If the diameter is x, the radius must be equal to half of it. That is to say, the radius of this semicircle equals to x over 2 units in its length. We define the center of this semicircle, this point as point O. So the radius OA equals to x over 2 units in its length, and the radius OD also equals to x over 2 units in its length. So in the drawing, we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally, and this point S. And now we have an external notch between two circles or semicircles or quarter circles. You can implement rule 10. So I'm speaking of rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. So in the drawing we have two circles, and those two circles touch each other externally at this point P. That is to say, they have an external notch between them at point P. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally, this point S. Therefore, we can implement rule 10. The center of this semicircle is here at point O. The center of this quarter circle is here at point C. And the straight line that connects the center together is of course the straight line OC. And this straight line OC must pass through point S, that is their touching point. Again, the straight line OC must pass through their touching point, that is point S. Or OSC is one straight line. And OSC is one straight line according to rule 10. If OSC is one straight line, it means that OC must be equal to OS plus SC. Again, OC equals to OS plus SC. So OC equals to OS. OS is the radius of this semicircle, that is x over 2, plus SC. SC is the radius of this quarter circle, that is equal to x. So in total, OC equals to x over 2 plus x, that is either 1.5x or 3 over 2x. So we found out that the length of line segment OC is 3 over 2 times x units in its length. In the next step, I copy the right triangle ODC in a new page, and we implemented the Pythagoras theorem on this right triangle ODC. So okay, this is the right triangle ODC that I copied from the original drawing. Side OD equals to x over 2 units in its length, DC equals to 5 units in its length, and the opponent OC equals to 3 over 2 times x units in its length. According to the Pythagoras theorem, in this right triangle ODC, OC squared, that is the square of the hypotenuse, equals to OD squared plus DC squared. OC is 3 over 2 times x, therefore OC squared is 3 over 2 times x squared, that is 9 quarters x squared. And it is equals to OD squared. OD is x over 2, therefore OD squared is x squared over 4. Plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total we should find out that 9 quarters x squared equals to 1 quarter x squared plus 25. Here we subtract x squared over 4 from this equation, and finally found out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared. X squared over 4 minus x squared over 4 is 0, so here we're left only with 25. So we found out that 8 quarters x squared equals to 25. 8 over 4 is 2, so this expression equals to 2x squared, and 2x squared equals to 25. Here we divided this equation by 2, and finally found out that x squared equals to 25 over 2. Here we took a root of this equation, and finally found out that x equals to 5 over square root of 2 units in its length. Our mission is to find out the area of this green shape. Repeat again, our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see. That the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Repeat again, the area of the green shape equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. What is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. The length of this rectangle ABCD is AB, that is 5. The width is BC, that is x. So in total, the length times the width is 5x. So the area of rectangle ABCD is 5x minus the area of the semicircle. What is the area of the semicircle? We know that the radius of the semicircle is x over 2. Therefore, the area must be equal to pi x over 2 squared divided by 2. Repeat again, the area of the semicircle equals to pi over pi times x over 2 squared divided by 2 minus the area of this quarter circle. What is the area of this quarter circle? We know that the radius of this quarter circle equals to x. Therefore, the area of this quarter circle must be equal to pi x squared over 4. So if we found out that the area of the quarter circle equals to pi x squared over 4. So actually, the value of this expression is the area of the green shape. What is the value of this expression? This equals to 5x. Here we have minus x over 2 squared. X over 2 squared equals to x squared over 4. And therefore, in total, this expression equals to pi x squared over 4 times 2. Equals to minus pi squared over 4 times 2. Minus pi x squared over 4. Here we have minus pi squared over 4. So the area of the quarter circle equals to 5x. Here we have minus pi x squared, and 4 times 2 is 8. So in total, this expression equals to minus pi x squared over 8. Here we have minus pi x squared over 4. Here we multiplied both the numerator and the denominator of this expression by 2. And we got that this expression equals to minus 2 pi x squared over 8. So there, the green shape equals to this expression. So this expression equals to 5x. And here we have minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total, we have found out that the area of the green shape equals to 5x minus 3 pi x squared over 8. But we already found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2. Therefore, we can substitute x in this expression by 5 over square root of 2. And you can substitute x squared in this expression by 25 over 2. We did it, and we actually found out that 5x and x equals to 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared equals to 25 over 2. So in total, we found out that the area of the green shape equals to 5 times 5 is 25, so in total this expression equals to 25 over square root of 2. Here we have minus 3 pi over 8 times 25 over 2. So in the numerator of this expression we have minus 3 pi times 25 is minus 75 pi, and 8 times 2 is 16. So in total, the value of this expression equals to 175 pi over 16. So in total, the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. or in terms of numbers, the value of this expression is equal to 2.95 square units. In conclusion, we found out that the area of this green shape equals to 2.95 square units. Okay, thank you very much.